Hey everybody. Today we're getting started with hypothesis testing for the mean, specifically in the situation when the population standard deviation sigma is known to us. A hypothesis test quantifies how plausible a single possible parameter value is in light of a random sample. In contrast, a confidence interval uses a random sample to give a range of plausible values for that parameter. Basically, a hypothesis test is useful when there's one parameter value of interest, one possible parameter value of interest. So throughout this vid, we're going to be considering this example. The manufacturer of a certain brand of chocolate bar advertises that on average, their chocolate bars weigh 350 grams. I worry that they're overestimating this, shorting us on our chocolate, so I weigh 10 of the bars and I find a sample mean of X bar equals 347. So obviously 347 does not equal 350, and there are two possible explanations for the difference between the advertised mean of 350 and the sample mean of 347 that we actually observed. First of all, the advertised mean could be wrong, and it's possible that the company really is just giving me less chocolate than they said they were. The second possibility is that the advertised value is correct, and the sample mean that I got, 347, is just low by random chance. I just happened to get unlucky with the 10 candy bars that I bought. The point of a hypothesis test is to distinguish between these two possibilities. A hypothesis test for the population mean mu does this using the central limit theorem. And very roughly, that says that X bar is approximately normal with the same expected value as the population that you're sampling from and a variance that's scaled down by a factor of 1 over n. So the standard deviation is scaled down by a factor of 1 over the square root of n. The central limit theorem says this approximation is better for large n. Sometimes you'll see the number n equals 30 as a rule of thumb, but it's reasonable for much smaller n, including n equals 10, if the population you're sampling from is pretty symmetric and doesn't have any extreme outliers. And those are reasonable assumptions in the case of these chocolate bars. To say that a little bit differently, we can write the sample mean X bar in terms of its z-score. So we subtract off the expected value mu, divide by the standard deviation, sigma divided by the square root of n, the standard deviation of X bar, that is. And that quantity, that fraction on the left, has the standard normal distribution. So to run a hypothesis test, we assume that the claimed parameter value, which we sometimes denote with mu sub naught, we assume that's true. We go out, we collect a random sample, and compute the z-score of that sample mean that we observe, using this formula that we just saw. If the claim is plausible, then we should get a z-score pretty near 0. And if the claim is implausible, we're going to get a more extreme z-score. The first step in this process is always to assume that the claimed parameter value is true. And we call that the null hypothesis, labeling it with a capital H sub 0. So in this example, the null hypothesis claim is that mu equals 350. More broadly, we might write mu equals mu naught. The null hypothesis always represents the single parameter value of interest. And oftentimes, it's a value that we have reason to suspect might not be true. And I think in that sense, this chocolate bar example is exactly typical. While we're at it, we should also specify the thing that we think might be true. In other words, a contradiction to that null hypothesis. In this example, it would be that the mean weight of all the chocolate bars is actually less than 350 grams. And this is called the alternative hypothesis, labeled H sub A, and this is the thing that we're hoping to gather data in favor of, the thing that we think is actually may be true. Between the null hypothesis and the alternative hypothesis, only one of those two can be true. They're contradictory. Notice that both of these hypotheses only refer to parameter values. They're making statements about the population, not the sample. And in particular, there's no sample data in here whatsoever. As a general rule, hypotheses should always be set before sample data is even collected. At minimum, it needs to be considered before the sample data is explored and analyzed. If you do that, if you look at the data and then go back to try and set your hypotheses, you're going to get meaningless results. That's considered to be a form of statistical malpractice. Once the hypotheses are in place, we use X bar to judge between them. In other words, we use the sample data to judge between statements about the population parameter. But more specifically, given H naught, we ask how likely is it that we would get a random sample mean so low? Mathematically, that means computing the probability that X bar is less than or equal to 347 given the population mean of 350. So remember, the population mean of 350 is assumed that's the null hypothesis value, so we just take it for granted when we're doing these calculations. This probability that we're going to eventually get is called the p-value of the test. And a low p-value indicates that when the null hypothesis is true, a sample like the one we got is actually very unlikely. So in that sense, a low p-value gives you stronger evidence against the null hypothesis and therefore in favor of the alternative. Coming back to our chocolate bar example, suppose that the population standard deviation in the candy of those candy bars is 4 grams. The null hypothesis value is 350 and the sample mean was 347. So plugging in, we can compute a z-score for that sample mean of about negative 2.37. So if the null hypothesis is true, the data that we got is about 2.37 standard deviations below what we would have expected for a sample mean. We call this z-score a test statistic. It quantifies how far the sample is from what was predicted by the null hypothesis. And we can use that to compute the p-value of the test, the probability of getting sample data less than or equal to what we got, given the null hypothesis. A test statistic should always have a well-known distribution, so probability calculations can be done directly using technology such as R. In this case, the test statistic has a standard normal distribution. We're talking about z-scores. In R, the command to compute in a standard normal distribution, or any normal distribution for that matter, is pnorm. So we need to use the code pnorm of negative 2.37 to get the probability of randomly getting a z-score less than or equal to negative 2.37. I've also given you a picture here showing the probability that we're trying to calculate. In this case, we get about 0.0089, pretty low probability score. It's important not to lose sight of what the p-value actually means. In this case, it means the probability of getting a sample mean no greater than 347 grams if the null hypothesis is true. That is, if the mean weight of all the company's chocolate bars is actually 350. If H0 is true, if the null hypothesis is true, a sample mean like this or less than this only happens 0.89% of the time, so not very often. It's unlikely, although possible, that this would happen by chance. So we're left with exactly 2 possibilities. Either something unusual happened, sample means like ours happen less than 1% of the time, or the null hypothesis isn't actually true like we originally assumed, and the company is actually producing chocolate bars that weigh less than 350 grams on average. In this particular case, our p-value of 0.0089 is very low, so it makes sense to choose the second option. We reject the null hypothesis and support the alternative hypothesis. Our conclusion is that there's good evidence for that alternative, that the mean is less than 350 grams. In other words, we have good evidence that the mean weight of this brand of candy bar is less than what the company advertises. Now, there are a number of questions still to be addressed in the conversation about hypothesis testing. First of all, we said that the p-value of 0.0089 was small, and it's worth thinking more explicitly about how we decided that that was a small number. Just how small is small enough before we reject H0? Would 0.02 qualify as a small p-value? What about 0.20? Thinking about this is going to lead us to the idea of statistical significance and the significance level of a hypothesis test. Secondly, the alternative hypothesis that we used in this example, mu less than 350, isn't exactly complementary to the null hypothesis that mu is 350. So why didn't we use an alternative hypothesis that does exactly contradict that null? And if we had done that, how would our calculations have changed? So as we get into this, we have to start thinking about the difference between a one-sided alternative hypothesis and a two-sided alternative hypothesis. Finally, at the beginning of this whole process, we assumed that the population standard deviation was known, and in particular, in this example, we assumed it was sigma equals 4 grams. But in practice, we don't tend to know that parameter any more than we know the population mean. So what should we do in that case?